you for the introduction. Welcome, everyone. Good afternoon. My name is David Pons. I'm a Senior Application Engineer at ANSYS. I'm going to be talking today about the ANSYS Thermal Fluid Solutions. Basically, show a general overview of the kind of solutions that we have for the thermal applications. So the agenda for today, going to be showing an introduction, what is computational thermal analysis, a little bit about engineering simulation for thermal analysis itself, the ANSYS advantage, really showing what makes us different, ANSYS as a company. And then at the end, I'm going to show some case studies and a final demonstration on a one-way FSI problem. So what is computational thermal analysis? Computational thermal analysis refers to the thermal analysis of engineering systems using numerical methods. This by nature is multidisciplinary. So really, when we go to analysis, we'd go to do a thermal analysis, energy is converted into heat in the solids and the fluids, and there is obviously interaction in the heat between those, the solid and the fluid. So really, in order to do a thorough analysis of this type of systems, you need to look at the two disciplines coupled together as one. Now, traditionally, these different disciplines have been treated as separate fields, but as more complex designs are needed and more in-depth and accurate solutions are needed to be found, this is no longer an optimal solution. So therefore, we need better accuracy, and we need to look for a solution that can easily couple the two different fields and two different disciplines together, and do so in a very efficient manner that makes sense for both large and small scale operations. And so why is computational thermal analysis important? It makes it important because it makes it possible to couple both mechanical fluid and also electromagnetic analysis, which again, it's very important in order to get accurate solutions for these complex problems that we deal with today. So is it really that important to use multiphysics for accurate solutions? A lot of the problems, again, are inherently coupled. So really, we need to look at the problems coupled together in order to get an accurate solution. Here are some of the examples that I would like to show where doing a thorough analysis, looking at the coupled physics, it's essentially important in order to get accurate solutions. For example, here the shuttle Challenger O-ring failure, SR-71 skin gaps at standard conditions. When we go to analyze gas turbine blades, the cooling system, and also designs, these are problems that are inherently coupled with the thermal and the fluid solution. Also for a reentry capsule, things like TPS and ablation, these are all problems that are very complex and that need to be analyzed in a coupled manner. So the ANSYS is different. What really makes ANSYS stand out in this environment? One of the things I like to call out is the integrated ecosystem. So really, when we go to analyze, do thermal analysis, both coupling the mechanical aspect and the fluid aspect, it's really needed to have a solution that you can couple the two areas together, but also you need to think about the design process. And really, as an engineer, we're looking for the most optimal way to solve a problem and the most efficient way to do so as well. So really coupling the design aspect of it also in cohesion with the physics aspect, really it's what defines the type of workflows that we need in order to solve these problems efficiently. ANSYS, we offer a comprehensive multiphysics simulation platform that really allows us to couple all these different physics together as one as a single software package. And also we can do things like inbuilt parameterization and optimization of the different geometries, and also customize the workflows in order to make them more user-friendly and easier to work with. Here I'm going to show some examples on ANSYS thermal analysis, how we can solve some of these complex problems related to the aerospace and defense field. One example is combustion. These are all simulations using our own software. Things like film cooling. So here we're showing a first vein for a turbine. It's showing the propagation of the film as it goes out from inside the passage of the airfoil itself. Things like thermal stresses, icing, where we can look at not only the deposition of the ice inside the surfaces, but also the crack propagation within this ice that was formed. Things like aerothermodynamics and hypersonics. Here in this animation, showing the use of the new scripted meshing workflow where this mesh for the simulation was generated as part of the using the polyhedral core method, which we're going to be talking about a little bit later. Things like nozzles and plumes, impinging jets, inflation, complex displacement and overset meshing. So this particular problem, we have a moving body within a set mesh. So something like this is very complicated to mesh, and it could be very time consuming. However, using the overset meshing technology that we're also going to showcase in a little bit, we can solve these problems much more quickly and efficiently. Also things like phase change, boiling and evaporation and things like that. And also electronics cooling. These are by no means all encompassing. These are just some examples of cool things that some of the solutions we can come up with using ANSYS software. But really it's not by all means all encompassing or everything that we can do. There's a lot more. There's only enough time to showcase everything. So if there's any particular questions or applications that yeah, I'll be more than happy to get engaged in that discussion. So really the key aspect here is that we like to drive innovation and productivity with ANSYS. So we provide the whole integrated ecosystem that allows you to go design and not only design but also analyze very complex problems. So beginning with full feature design tools, we have a whole long list of different design tools that you can use to for very specific applications. For example, SpaceClaim Vista tools, Blade Model, Blade Gen, Turbo Grid for turbo machinery, fluid meshing, and so on. We have world-class fluid simulation software such as CFX and Fluent. Well, there's some others. We have the world's most extensive material library, ANSYS Granta. We have robust design with structural and thermal analysis tools. So we have, using Workbench, you can seamlessly integrate ANSYS Mechanical or even LS Dyna to do the coupled structural analysis. And our example today is going to showcase a little bit on an example of that. Also, we have full collaborative workspace using ANSYS Minerva and Workbench, which also have a slide on the next. And finally, you can optimize the design using ANSYS OptiSlang. So you can full integration with all the ANSYS simulation tools, and you can conduct multi-objective and multidisciplinary optimizations with ANSYS software or other external third-party software. It's not necessarily limited to ANSYS software. But the fact that we can have everything as a single package, very efficiently transfer data sets and transfer different simulation packages together couple them together makes it very, very useful. So I'm going to be talking about some of the state-of-the-art meshing technologies that we have recently incorporated in some of their recent releases for ANSYS. The first of them being scripted meshing workflows. So we have incorporated a task-based workflow that accelerates the meshing process. This is completely customizable and scripted. So once you develop the optimization loop on the script, it's completely hands-off approach, and it generates a very complex mesh and very high-quality mesh as well. You can embed it all the best practices for each task. So really, once you develop the script, once you develop the workflow, it can be deployed across different organizations or different groups, and you can have a completely hands-off approach to generating a mesh. And it also can be done process in batch. So it can be completely transparent, and so it's taking really the guesswork out of meshing. Another technology that we'd like to showcase is the Mosaic polyhex core mesh. This is a patent pending technology where it uses a hexahedral dominant core mesh using perfect cube elements. And also this allows you to reduce phase count and lower the memory requirements while also increasing significantly the mesh quality. And another thing is parallel scalability. This Mosaic polyhex core mesh has been completely parallelized. So you can scale it up to 256 cores, and you can generate up to 10 million cells per minute mesh generation. In one particular example, in working with a client, we were able, using the polyhex core mesh and the scripted meshing workflow in conjunction, we were able to provide 20% speed up in meshing and up to 30 to 50% reduction in solve time as a direct result of using these two technologies together. And moreover, we were able to provide with more accurate results than the traditional method that they were using. So this is something that's we're very, very excited to showcase today. Some of the others meshing technologies that we'd like to showcase is the overset meshing. I showed an example of this previously, where we have this torpedo launching off of the silo. In order to analyze something like this, it would be very complex, because at every different time step you would need to, with the mesh with the body motion, you would need to compute a new different mesh or provide a mesh adaptation. However, with the overset mesh, really you create a mesh for the entire domain outside, and then a separate mesh just for in this example, for the torpedo. And then what the overset meshing does is interpolates the two different solutions together, the two different meshes, and then it allows you to really simulate these complex fluid flows that have large relative motion. It really runs very, very fast because there's no need to recompute the mesh. The code automatically moves the mesh relative to each other and does the interpolation kind of behind the scenes, but there's no remeshing needed. So there's a lot of improvements in terms of speed. Things like part replacement are also very useful to do this, because then you would need to generate just one single large domain mesh, and then have a separate mesh just for the component itself that you're going to replace. And then that makes it really easy to just move it around or replace parts. Also conduct things like design exploration studies. Here in this example, we have an example of the overset meshing technology using on a complex compound wing. Here you can kind of see the overlay of the two meshes. So we have one mesh for this region here, that leading edge, and then a separate mesh for just the entire domain outside. And really, with the interpolation, one mesh moves relative to the other, and then the code automatically takes care of interpolating the solution in between them. Sorry about that. Also, another technology that I would like to focus on is the mesh adaptation. So here we have a volume of fluids to DPM mesh. the discrete phase model. So this this model itself tracks the liquid gas interface with the discrete phase model, and then it tracks the discrete particles and converts them to um, point masses. So really, what this allows you to do is to start with a very coarse mesh, and you're able to um, simulate this complex spray problem with mesh adaptation. Slide. Next, we're going to talk about advanced physics modeling, some of the improvements that have been done to the recent in the recent releases for in the areas of physics. The first one being the stress blended eddy simulation, which is a hybrid RANS LES framework. That really allows the resolution of detail on steady flow. So the idea here is that it uses RANs in areas where resolution is insufficient, for example, near the walls, and then in the other areas where you can have enough resolution, uses LES, and then there is an automated transition between the two by using a shielding and a blending function. This really allows you to get an optimal blend of speed and accuracy between the two for the turbulent flows. In this example here, we have a flow over a wedge, and we can see that using the SBS model really provides useful for these types of applications. The next technology I'm going to talk about is the generalized K omega two equation turbulence model, or GECO. This is a two equation model that has actually 5 different coefficients embedded into the code that the user can fine tune for their specific applications. So really, the idea is to eliminate the multiplicity of the 2D equation models and just have one single model that will suffice for most applications. Obviously, the user can fine tune using these 5 constants to fine tune for the specific applications, but more importantly, you can use the different sets of coefficients for different parts of the flow domain. So you can really tailor the turbulence model to be more to behave the way you want it to in different parts of the flow field. Here in this diagram, we're showing a flow over a back-facing wall. In this region where you have a lot of recirculation, separation of the flow, and we're looking at the computed shear stresses and heat transfer on the wall using the GECO model. We can see that compared to a lot of other turbulence models, the GECO being the blue line shows the most best match with the data. Another thing we'd like to showcase is the parametric design and adjoint methods. With a software like the Design Explorer and also OptiSlang, we can conduct parametric design optimizations and conduct DOE experiments and produce response surfaces. This is something that's actually very straightforward to do using either of the two softwares, and we can generate response surfaces to for reduce order modeling and things like that. Also, in conjunction to that, but separate, is a shape optimization with the adjoint methods. So it uses a gradient-based optimizations to find an optimal shape. The advantage of this is that there is no need to specify the parameters up front. The solver already determines which parameters are more sensitive to drive the approach to improve the design, and it does it automatically. The optimized geometry can be exported back to a CAD and an SDO file, and really this adjoint method it has a very low investment in computation time, so it runs very fast. And also, interestingly, this can be used in conjunction with the overset meshing that we showcased before. That can be really useful uh, for optimization, shape optimization. In this example shown here on the right-hand side, we have an error spike that was modeled using the overset meshing technology. And then the adjoint method was used to optimize the shape of the disk itself. And with the adjoint method, here is it showing the original shape, and then here's the optimized shape. And we found that there was a 2% reduction in vehicle drag just by optimizing the shape of the disk itself. So it's a very, very powerful tool that can be used for a lot of different applications. And lastly, we'd like to talk about the ANSYS simulation platform, software called Minerva, which is a centralized simulation knowledge management application. It does things like dashboard reporting, data section, metadata report, and lightweight visualization, configuration management, local application launcher, job submission, collaboration, task and work requests, and integration with ANSYS Workbench. So it's really like one-stop solution to integrate all the different configuration and knowledge management. So you can integrate things like all the different design tools, all the different geometries, all the different disciplines can be handled that manage that data simultaneously in one centralized location. And it's not limited to ANSYS products, so there's vast integration with third-party applications. Okay, so at this point, I would like to talk about the case study. The first case study I want to talk about is a thermal FSI analysis of a large caliber projectile with integrated avionics. So we have this particular problem. It's a supersonic spinning projectile that has integrated avionics inside. So this projectile is moving in Mach 4. It's spinning at 30,000 RPMs. And there is a avionics system inside with a heat source, a specified heat source. And there is also a fan inside that is meant to provide cooling for the avionics. So really, we're looking to, number one, determine the optimal fan configuration that will provide adequate cooling for the internal avionics system. Characterize the air loads acting within the flight envelope, and also improve the loads by optimizing the external shape. So I'm going to show how we could solve a problem like this using our solutions. Using ANSYS Workbench, you can integrate the different physics easily and conduct a parametric optimization, which is what is done here. So with Workbench, you have this window, and then you drag and drop different components for the different physics that you want to solve. So here you start with your CAD geometry. Then this is passed over to a mesher, which can be fluent mesher or any other meshers that we have, and then set up for a CFD solution. So in the case of the fluent meshing with the scripted workflows, this could all be completely automated. So once you bring in the geometry, you can map that into the fluent and be ready instantaneously for the CFD solution. And then lastly, you add a results block where you can analyze your results. And then all of this is grouped, it's driven by the goal-driven optimization. And this component here is actually what drives the optimization and looks for the optimal solutions. With the scripted workflows, we can generate a high quality mesh for both the external domain and the internal domain. It can be done very, very easily. So once the main CFD solution was run, he conducted conjugate heat transfer analysis in Fluent, and it shows contours here of the temperature, a Mach number, a cross section of the temperature inside of the projectile, and also the fan cooling of the avionics system. These are all results of the actual CFD simulation. And then the first thing we want to look at is the optimization of the temperature of the avionics system. So you can easily conduct a design optimization to find the optimal fan location and sizing that's going to provide the lowest surface temperatures. The idea is to parameterize the location of the fan and the size itself, the mass flow across the fan. And then the optimizer, or the DOE optimizer, conducts a DOE and generates a response surface automatically. There's no need to export the data in any way and manipulate it. This is all done automatically, and you can quickly see a response surface. And with this method, you can easily gather the optimal location of that would provide the lowest surface temperature, given the constraints. Similarly, you can do the same for characterizing the aero loads with respect to height and the velocity. So the parameters are like altitude, which is going to dominate the pressure, and then the velocity can be part of the DOE experiment. And then you can use that to characterize the drag in the moment acting on the projectile itself. Then this will results from this analysis, you can use it to either down select relative relevant conditions for this shape optimization project, or also you can use it to develop your own reduced order modeling or lower fidelity analysis. Finally, the last item here, we wanted to look at the optimization of aero loads with respect to the groove length and depth. So we want to optimize the shape of these grooves on the external surface. So what we did is parameterize the model using the length and the depth as two different variables. And then we conducted a DOE experiment on that, where we can see the results on the right-hand side, showing the drag in the moment as the direct results. And then from this, we can down select the optimal design based on the constraints that we have. So we can see that it's very, very easy to conduct these type of analysis, this coupled multiphysic analysis using the Workbench and the different ANSYS tools. So we provided a thermal FSI analysis of a large caliber projectile with integrated avionics using Workbench. So we can use either design model or SpaceClaim to create the geometry. Use fluid meshing with the water technical workflow to generate the mesh. The solution was obtained using Fluent, and the results are processed with CFD Post. And finally, the Design Explorer was used to optimize the fan configuration and also the external shape of the projectile. At this point, I'm going to go into the demonstration. The first demonstration I wanted to show is the scripted meshing workflow. I'm going to show a video just to, for ease of use. I have a already recorded video showing how easy it is to generate a mesh for a generic combustor, gas turbine combustor. So really, once you have Fluent and you have your script generated, it takes care of everything. It loads in the geometry and then performs the mesh completely hands-off. And this video is actually running in real time. It's using 32 cores for this particular application, using the polyhex core meshing technology. So really, as we speak, we can see that it's going to generate about 16.5 million elements in less than 3 minutes, and all completely automated. And the fact that it's scripted and it's completely hands-off. So if I were to make any design changes to the CAD geometry, the same script would apply because it's using the name selections, and it makes it very robust and very easy to make design changes on the fly, and then you can easily adapt and generate new meshes as needed. So at this point, the mesh is complete, and we can see that generates a very high quality elements. I'm using the hex core technology. And for this particular application, using local refinement. So there's additional refinement in the combustion region where it's needed to resolve or large edge simulations. And then in order to save mesh on the outside region, the panels outside, it's using a coarser mesh in order to save memory requirements. So this is an example of really how we can use scripted meshing workflow. It's very, very robust, very, very useful for these type of applications. Okay, and then at this point, I'm going to be switching back to the, I'm going to be going to the presentation, going to the hands-on demonstration of conducting a one-way thermal FSI demonstration for a hyperbolic flare at Mach number close to 10. So this example, I'm going to show the setup of a one-way FSI problem for a re-entry hypersonic vehicle by coupling both the pressure and the thermal loads from the CFD simulation into a structural thermal model. So we're going to be mainly looking at not only the solution for the flow field around the vehicle, but also calculate the stresses and the deformation in the aeroshell at these extreme conditions. So for this particular problem, I'm going to make some assumptions and simplifications in order to, for the purposes of the demonstration, to make them easier to solve. But the general concept applies to for a more complex approach. The first simplification that we're going to do is we're going to be solving only a 20-degree slice of the body. So this means that we're assuming that it is at a 0-degree angle of attack. So then that allows us to simplify the model by looking only at a wedge of the solution. The next simplification is that the air is behaving like an ideal gas, so there's no reaction. However, in this case, such high Mach number, the total temperature is high enough that dissociation and ionization of the air could take place. However, for the concept of this demonstration, we're not gonna assume it's an ideal gas. And finally, the material of the vehicle itself, it's going to be steel, which is generally unrealistic since there will be different TPS layers in the outer surface, which we're not going to model in this particular case. However, there's nothing that would prevent us to being able to conduct these a more complex simulation without having these simplifications. This is just for the concept of this demonstration. We decided to do it this way. So then the first thing we're going to start with, similar to what we showed in the scripted meshing workflow, once you have the CAD geometry with your name selections, which I'm going to show. So we're starting using SpaceClaim. We have this problem, which is the 20-degree wedge that I was showing before. So we have three different bodies. So we have the free stream fluid, the solid, and then finally the interior fluid itself. And then all of these different zones have been identified using name selections. So we created a name selection for each of the different areas that we're going to use for the setup of the simulation. So we have our periodic faces, the free stream inlet, the outlet, on the different walls for the solid and the cabin side, and also the walls that are in contact with the fluid itself. Once this has been generated, it's actually very easy. We then take this, pass it over to within Workbench. So we have this geometry block, and then we pass it over to the Fluent with Fluent meshing, and we go and generate the mesh. For this demonstration, in order to save time, I went ahead and already have this CFD solution already generated. But really, the process of setup, once you have the scripted workflow, it's very easy in order to get a solution. So we're assuming that we already have a solution. This is the CFD results from that particular problem. We have a temperature contour showing on there, and some of the residuals in a monitor for the max temperature, so we can see that the maximum temperature is no longer changing as it was iterating, and the residuals were low enough, so we consider the case to be well converged. So then, starting from this point, then we can go ahead and do the FSI problem. So then at this point, I'm going to grab a what's called a static structural component and drag it onto Workbench. And then this already has pretty much goes through a list of things that are needed in order to conduct the analysis. So then I'll take the solution from my CFD simulation and pass it over to the setup. And then this is going to already map the thermal and the thermal and the pressure loads into my structural simulation. And then my geometry, I'm going to pass it on as well. And then it's going to be coupling the geometry. One assumption that we're going to making is that the material properties are going to be steel. In this case, engineering data. Here I'm using structural steel, but however, if I were to use the different materials, then I can easily set it here or change any of the material properties. But for the context of this demonstration, it's going to be using the default. And then I'm already set in order to run the simulation, so I can load in my static structural model using this ANSYS Mechanical. Taking a minute to load. It's loading right now. Popped up on a different screen. Okay. So here we have in ANSYS Mechanical, we have the geometry as it came in. However, we're not concerned with any of the fluid regions. So we're going to suppress these geometries bodies. So the friction fluid, I'm going to suppress it, and the cabin fluid suppressed as well. So then now we have just the solid itself, just what we really care about in the context of the simulation. Then the next step is to generate the mesh itself. For this, are we going to use all the standard configurations, and it already have a mesh all ready to go. Then the next step is to import the loads itself that came in from the CFD simulation. So here we go. In this tree, go to imported load, right click, insert body temperature. And then for the geometry selection, I'm going to select the entire body, then apply the temperatures. And we already see that they are mapped in. and then finally going to go import load. And it's doing the mapping. So now at this point, it does the interpolation of the temperature values. Similarly, you're going to do the same for the pressures. So import the pressures, and then in this case, I'm going to select the surfaces because the pressures act on the surface itself. Then we apply the pressures. We load those in. Again, it's doing interpolation between the CFD solution and the thermal model that we have. And now we can see that they're already set. Finally, the last point is to add the boundary conditions. So, static structural. So I'm going to insert here a fixed support. So we're going to be assuming that this back wall here is fixed. So in geometry selection, we're going to do a name selection, and then you use the wall solid. This wall solid is going to be a fixed support. We're also going to suit the frictionless support for the periodic sides. So we use the name selection that we generated in SpaceClaim and do periodic 1. And we add a second one for the other side. Frictionless support. And now we have our boundary conditions set. At this point, all that's needed then is to run the simulation. Before we do that, we want to insert what we want to look at the total deformation and the stress, equivalent stress. And then we go to solve. And this point, we're running at the one-way FSI problem using the mapped temperatures and pressures from the CFD solution into my thermal model. And we already have results. Look at the contours of the total deformation and the equivalent stress acting. Finally, we can do is we can go back into Workbench. We can bring in both results together, so I can create a CFD post, and then I can pass over the static structural solution as well as my CFD solution together and load that, and it's what we've shown here. So now here we have the deformation, the total deformation from the thermal solution, and also we can look at the CFD results as well. So here we have both the displacement and the CFD results for this particular solution. So that way we can see that how easy it is to do this type of problems. And similarly, we can do follow the same approach using Workbench and so on to do a lot of these problems that were shown today. So we took the common geometry and we used scripted meshing for generate the mesh and get the fluid solution, map the solution onto the thermal model, and get the thermal stresses and total deformation. And with this, we conclude the demonstration. Finally, I would like to invite you to look at our website, ANSYS. We have a series of NASA webinars that we have put together, showcasing a lot of different problems for these type of applications. This most recently, just yesterday, we had a heat flux measurements in hypersonic environments webinar. So, and there's a lot of really cool information there. Some simulations that were done for COVID to assess the particles inside of our aircraft cabin and so on. So I invite you to go there and check them out. And then with that concludes my presentation. I don't know if there's any questions at this point. If not, then I'll thank you for your time, and I'll pass it over to the NASA staff.
Great. Thank you so much, David. I really appreciate your presentation. I don't see any questions in the chat right now. We can wait a few minutes if anything pops up. Otherwise, we'll make sure to... Oh, I have one question from Jody. Says, she heard you talk about coding to input information into ANSYS. Do you write this code in ANSYS or another program?
There's different approaches that you can, depending on what exactly it is that you want to do. But we have a Python API that you can develop a lot of the integration with different tools using Python. So then we can use that to couple with third-party applications or third-party data sources. Also, for within Fluent itself, for the scripted workflow that we showed here, it's using a combination of the journal, traditional journal method, which uses scheme language, and Python.
Great. We have another question from Clark. He says, which analysis system is combustion done in? Is it in Fluent?
Yes, this particular example that we showed is using Fluent.